Talking about thus far is how to figure out how to construct the parse table for some sort of LR parser, right? So we talked about constructing these LR0 items and constructing the NFA from that, converting that NFA to a DFA. So if you remember, for each item, the NFA had a state, right? When you convert that, when you go from that NFA to a DFA, each state of the DFA is a set of LR0 items. And what an LR0 item looks like is it's a production with a dot on the right-hand side. That serves to divide up the right-hand side of the production into two parts. One part says what the parser has seen already, and the other part gives a possible continuation or legal input. So if I now have, let's talk about NFA states for a little while, okay? So if I have an NFA state that has an item like this, and that's a token, then I know that if I'm in this NFA state, or correspondingly, if I'm in a DFA state that has this item and possibly other items, then in that state, I have seen something that could be derived from alpha. So one possible way for the parse to proceed would be to next see something derivable from A beta. And since A is a token, in this situation, if I do see the token A, then I can say, OK, so far things look like we are on track on this. I will shift that onto the stack and keep going. So the shift actions are, in some sense, inevitable. You look at this, the state, and you say, well, if there's a token at this point to the right of the dot, and I see that token, I have a shift action. Shift, and then move on to whatever state this one is. Keep going. So the issue arises as to what happens when I've shifted all the way across, walked the dot all the way to the right, and at that point, I have to reduce. The question is, when should I reduce? Okay. The issue of when should I reduce comes up because my parser is using the next token in the input stream to guide its actions. So you could imagine the parser going along and saying, well, since I've walked the dot all the way to the right, it looks like a good time to reduce. Let me reduce no matter what the input token is. So you could have a parser that does that. For every token in your alphabet, you could say, if I'm in this state, for all tokens in the alphabet, I'll reduce. The problem with doing that is that that introduces reduce actions all over the place, right? So you can, if the parser just blindly, willy-nilly says, oh, look, I have my dot all the way on the right-hand side, so I'm going to reduce regardless of what the input token is. That means that I have a reduce action for every token in the parse table. So here's the structure of the parse table, right? Here's my parse table. Man, I wish I had one of these things that's actually right. So here's my parse table. Here's the action part, and this is the go-to part. And if you remember what the action part is, I index into the action part with the current state, which is on the top of the stack, and the next input token. So in the action part, this is, on this axis I have state, and on this axis I have tokens, right? So if I have a state where the dot is all the way across, let's suppose that in this state over here, I have something like A goes to alpha dot. The dot's all the way across. And let's suppose that I decide that I'm going to reduce no matter what. Then I have a reduce action across the board, all the way. Reduce, reduce, all the way across. So if any of these states, if any of these entries that has these reduce actions thrown in, if any of them also has a shift action, because some other item in this DFA state, this is a DFA state now, so I must have a B goes to, I don't know, gamma dot B something, right? If any of those other states has a shift action, then I'm going to have some entry that has a reduce action and a shift action, and I have a conflict. So that's the problem that comes from reducing too liberally. I can't do that. Well, I can, but that means that it potentially introduces spurious conflicts. So we have to be more discriminating. We can't simply say, oh, look, we managed to walk the dot all the way across, so let's just reduce no matter what. The problem is that that introduces too many conflicts. So what we can and should do is, in a situation like this, when I have a state where I've walked the dot all the way to the right, so that means I have seen the right-hand side of a production. At this point, I should ask, OK, can I use the next input token to give me some guidance on what's going on? Can I have that give me some guidance so that I have fewer reduce actions? I only introduce reduce actions where they're appropriate. And by getting rid of some reduce actions, I manage to avoid some conflicts. Okay? The definition of an SLR1 parser is that when I go through the parse table construction, I construct the DFA. So I now have states. Each state has a set of LR0 items. I look at each state. I look at the items in each state. I just go through the items and I say, OK, here's an item that introduces some reduce actions. Here's an item that introduces some some shift actions, reduce actions. OK? So I just fill them in. And if any entry in that table gets more than one action filled in, I have a conflict. That grammar is not SLR1 parsable. Okay, there are other LR parsing algorithms. At the end of the day, the main approach is the same. You fill in the shift actions, you fill in the reduce actions. If any entry in the parse table has multiple entries, has two different reduce entries, or one shift entry and a reduce entry, that's a conflict. That item is not parsable. That grammar is not parsable. So the key here is to cut down on spurious reduce entries as much as possible. Okay, to keep the reduce entries we need, but not introduce unnecessary ones, because they potentially lead to conflicts. So the next thought, if we want to cut this down, is to say, OK, let's look at the next input token and see if it can help us. See if that can help us cut down on the number of reduce actions, the number of unnecessary reduce actions. Now, ideally, what we'd like to be able to do is to say, look, here's my automaton. Suppose I'm an oracle. I know everything that's ever going to happen in the behavior of this automaton. And if I could have this oracle tell me the exact set of tokens that could show up during the parsing process in the input at this point, then I would be good. Right? Because then I could say, well, now I know exactly the set of tokens that could possibly show up when I'm prepared to reduce. And that would be a big help. The problem is that itself is hard to do. What we will do is do an approximation. So here's what we'll do. So the question we'll ask is this. Here's my start symbol. So I have a grammar, variables, terminals, productions, start symbol. And let's look at some derivation in this grammar. So I've applied the derivations. I have some variable A, and this guy goes off and obtains other stuff. And the question I ask is, when I am about to reduce by a production for this variable, So when I'm about to reduce, here's a production for this variable. What tokens could show up here? What tokens could we find here? Okay, immediately after A. The point being that when I'm, so going back to the construction of the parse table, if I can somehow compute which tokens we could see at this point, the next input token when we are about to do a reduce action must be one of these tokens, right? So if I only carry out reduce actions if the input token is one of these guys, then potentially I can cut back the number of reduce actions and hopefully avoid some conflicts. So this is the essential idea. This is called the follow set. Okay? So more formally, I have a grammar G. So given a non-terminal X in the set of variables, follow of X is defined as, let me speak it first and then I'll write down the notation. It's defined to be the set of tokens. So follow of X is a set of tokens. It's a set of tokens that could appear immediately after, immediately following that token, in that case X, in some sequence of grammar symbols derived from X. And it's the derived from X that's crucial here. Because if I wasn't worried about the grammar symbols that I could derive from the start symbol X, you could have anything follow X, right? If I just came up with arbitrary sequences of grammar symbols, anything could follow X. So the key point is, what can follow that grammar symbol that I care about in some derivation from the start symbol? Okay, that's what matters. So follow of X is defined as the set of tokens, the set of symbols in T, such that starting from the start symbol, in some number of derivation steps, I can compute alpha X A beta, where and alpha and beta are in V union T star. So I want you guys to look at that. It's early on a Monday morning, so I want you to stare at that for a while and make certain that what I've written down squares with what I spoke.
So V union T, that's the variables and tokens. It's some sequence of variables.
That's right. So V union T star means some finite sequence of variables and tokens. What does A underline mean? That's a good question. I underlined A to emphasize that it's a token. Because sometimes lowercase a and lowercase alpha look very similar. Right?
What's the star by the arrow?
What's the star by the arrow? That is derives in some number of steps.
Oh, okay. What's the star by the
Well, we're running out of stars, right? That is the Kleene closure. Do you remember what that is? You can take the fifth.
Any combination of them being in the empty set and any combination of any number of that set.
That's sort of kind of there.
Yeah.
Sort of kind of there. Let's go back and talk about the Kleene closure a little bit. Anyone else want to take a stab at the Kleene closure? Yeah.
It's all sequences of elements that were in that set, in that original set given.
Mm-hmm.
And it could be sequences of 0 remaining.
Yeah. So if I have a set, so given a finite set, let's say, I'm running out of symbols here, that shouldn't be the case. Let's say S. So this S is different from that S, okay? Given a finite set S, S star is defined to be something, and in practice is understood in similar terms. It's defined to be S to the 0 union S union SS union SSS, and so on ad nauseum. So S to the 0 is, okay. This is S concatenated with itself. So there's this. So these are all things concatenated with themselves. This is S concatenated with itself, and so on. S to the 0 is the empty sequence, which is different from the empty set. Okay? So that's the mathematical definition. And in human terms, it means it's the set of finite strings, the set of all finite strings we can construct using symbols in S. Okay? And because Kleene star shows up so often in formal languages, let me spend a little bit more time on it. Suppose I want to talk about all the works of Shakespeare, or all the works you can get by a room full of monkeys sitting and typing. What is the underlying alphabet S? Sure. Sorry? Let's, for the sake of, yeah, print, left bracket, colon, print, colon, right bracket. What is S star? The set of all possible strings. That's all finite strings. Okay. Suppose I want to talk about all finite bit strings. What is S? 0 and 1. So S star is what?
Every picture, every written, every program, everything.
Yeah, just imagine 0, 1, and star. It gives you that much. That's pretty powerful. All right. So come back over here. So I want you guys to think about what this says and what I said earlier before I got distracted with monkeys typing, and see if you can say this in English. What is it saying? Because if we can figure out what this is saying, then we'll be able to figure out how to compute it. If we don't know what it's saying, then we have no idea what we're computing. What is it saying? I know it's Monday morning, but by now you guys should be awake. Eric, you have your hands up. What's it saying? You were brushing your head. He was pondering. Brian.
Basically, we don't really care about alpha and beta because we're concentrating on X right now and A.
Right.
Anything that can be created with variables and tokens.
Mm-hmm. So Brian's saying alpha and beta, we don't really care about them. They're just placeholders. They are sitting kind of on the left and right. Do they even have to be there?
Yeah, we want to make sure it's valid with variables and tokens.
Right, but could it ever be the case that I have S goes to XA? Could alpha and beta not be there at all? So does that definition take care of that?
Yes.
How?
Kleene closure.
Kleene closure, what about it?
Well, it can be the empty.
It can be the empty string, thank you. So this allows alpha and beta to be the empty string. Excellent. Okay. So it's a set of tokens such that starting from the start symbol in some number of derivation steps. You guys know what a derivation is, right? You guys remember that. So in some number of derivation steps, we can get to some sequence of stuff. So that's now x. We can get to some sequence of stuff. This is alpha, that's beta, here's x, and that's the follow set we care about. Question?
How come x is part of the variable set, but not potentially the terminal set? Is it because variables include terminals?
No, variables don't include terminals. So for example, for the parser that you're writing for C++, what are the terminals? Can you name some terminals for me? Yeah, the tokens, right? They're exactly the tokens. So these guys are the tokens. And what are some of the variables that you have? Function, statement, declarations. Okay, so they're the things that appear on the left-hand side of productions in your YAC input. So we would never have a production that says intcon colon something or ID colon something, right? So the variables and the tokens are disjoint.
So when we say follow, I thought it meant like follow in the rule, like on the right side.
That's right. It follows over here.
So you're saying it follows the rule.
It follows the variable. So this looks like barbed wire. The reason we care about following, so let me back up. If we really wanted to, we could imagine writing up an analogous definition that says, what are the tokens that could follow a token? We could do that. The reason we don't, and the reason my definition presupposes that I'm talking about a variable, is that the whole point in defining follow sets is to help us figure out when we should reduce actions. Okay, so if you think way back when, we began by saying, oh, look, here's this approach to parsing, this bottom-up shift-reduce approach, where there's this magic table, and the table tells us, thou shalt reduce, thou shalt shift, whatever, right? The hard part in all of this is figuring out that table. If you can figure out the table, parsing is easy. And we talked about constructing the table some, and the part that is difficult is figuring out when to reduce. And in order to figure out when to reduce, what we're trying to do here is to figure out if I'm about to reduce with some production x goes to something. Okay, so here's, I don't know, this is x. I'm about to reduce with some production x goes to gamma. And the question is, what stuff could show up in the right of x? Okay, that's the reason, because at the end of the day, what we are trying to accomplish is to find out when we can reduce with x, so we can fill out this table without having too many reduce actions. Okay, so we can just fill it out the right places. That's the reason we're only computing follow sets, and we're defining it this way, and essentially restricting ourselves to variables. Does that help? I don't know if that answered your question. Okay, other questions? Yeah.
It's kind of unclear. It's like, so a follow set is not just a set of all productions that can go to the next step.
A follow set is not the set of all productions that can go to the next step. No, it's not a subset of productions, it's a set of tokens. A follow set is a set of tokens. Okay? So if I ask you, let's see. Let's think of, I've forgotten the details of the C++ grammar, but here's one, right? Prog goes to fun, prog, or deco. Of course, you guys would write this left recursive, so you don't get infinite, you don't run out of memory, or epsilon, right? So I ask you, what tokens could follow decal? Decal has other stuff, obviously. But over here, you'd say, OK, I can see that maybe there's other stuff here, but semicolon could follow decal. Okay? And maybe there's some other stuff along here. So if I ask you in general, what could follow a non-terminal or a variable, it's going to be a set of tokens like that. All right? Other questions? How are we doing on time? Okay.
So if there's
Yeah.
more than one way to get x, so there's lots of ways that we could
Mhm.
derive x. Suppose one of those ways includes a
Mhm.
after it, and one of those ways doesn't, and a is also a valid character after x.
Mhm.
And so at that point,
So I think the question is that if I have the following scenario. So suppose, starting with S, I go off, and in one direction I can have alpha, x, a, beta. So there's an a over here, and in the other direction I have S, stuff, x, something else, not a. Is this the
well, what I was saying is if x could be derived by some sequence of variables, tokens,
Mhm.
one of those included a at the end.
At the
One of
end.
at the end of it.
all the way at the end or just over here?
At the end of x.
Okay.
The other.
Uh-huh.
A is at the end, and then one of them was identical and didn't have a at the end.
Uh-huh.
So you could have that a be included in x, or it could not be included.
That. Okay, I understand the question. So let's think of a specific example. Let's suppose I have a simple grammar of expressions. Okay, so arithmetic expressions: e goes to e plus e goes to e times e, and e goes to integer constant. All right. So let's look at the parse trees I get from that. So here's one. This is nice because e is the start symbol, e is the grammar, the one variable that I have. E goes to e plus e. So here's the grammar symbol that I'm talking about. There's alpha. Can't see it. That's the token, and this is beta. Okay? So this guy is in follower V, right? But does plus always have to follow E in this grammar? No. Why not? You could get times. So here's a different production. Sorry, here's a different derivation. E goes to E times E. And here's E again. That's this guy. What can I say about that now? It's not plus. We can say that, but we can say more than that. What can we say? Stars in the follower V. So this is actually good because now we've just figured out that I have two different productions in the follower V. Not productions, two different tokens, right? Different productions, different derivations get me two different tokens. So we have something of an intuition about what follower V entails. This is the definition. And what this example shows you is that you can look at the productions, you can look at the derivations, and you can have more than one thing in the follow of a grammar symbol, of a non-terminal. Now in this case, we built a parse tree, and looked at the tree and said, oh, look, this guy follows this guy in this tree, and this guy follows this guy in this tree. Is it possible to get that information without building the parse tree? Because if you look at C minus minus, the grammar is so big that building parse trees and staring at them would take a lot of work. Could we figure out that plus is in the follow of E and times is in the follow of E without actually constructing parse trees? I've given you the grammar. That's the grammar. Those are the grammar productions right there. Eric.
Well, if we look at the grammar, couldn't we just say, okay, well, I know that sometimes plus is right after E, and I know that sometimes time is right after E, so both can follow E?
That's right. Thank you. So I could actually look at the grammar and say, hey, look, plus can follow E, and times can follow E. Isn't that good or what? So I don't have to build trees. So on that wonderful insight, let's take a quick break, and we'll come back and we'll talk about the actual algorithms.